Welcome to a walkthrough of a classic conservation of energy problem, or as we often call it, a roller coaster problem. Now, yes, this skateboarder is not on a roller coaster, but we call any of these where we have an interaction of gravity, height, and motion, where you're speeding up and slowing down as you're changing height. In other words, an interplay of potential and kinetic energy. We call all of those roller coaster problems. It is the fundamental idea behind the way roller coasters work. Our huge idea for this whole unit is that total mechanical energy, if we have no outside forces, and in this problem, we are saying there are no outside forces such as air resistance or friction in the wheels or anything else, if we have no outside forces gumming up the works, that the total energy in the beginning equals the total energy in the end, although it can transfer between potential and kinetic, but the total has to stay the same. So this is the same equation written out with our KE and PE, our kinetic and potential for the total, broken out so that these two in the beginning have to equal these two later on at 0.2 or 0.3. So again, the big idea we're going for here, because doing a grid for these points, as we have given you, is that if we figure out the total mechanical energy for any point along the way, then we know that that is the same total for all points. So once I figure out one total, I will know all of them. And that's what these equations are saying. Now, in order to work this kind of problem, we need to go through and do what I call an energy audit. Does it have a certain type of energy? And if so, can we calculate it? So for example, at 0.1, does this skateboarder have potential energy? Well, when we're asking that, we're really saying, do they have height? Well, at the beginning, the height is 0. And since potential energy is mgh, if the height is 0, then the potential energy is 0. Does the skateboarder have kinetic energy? Well, what you're really asking with kinetic energy is, are you moving? And yes, the skateboarder is moving. Next question. Oh, if this is not 0, do we have the numbers we need to calculate it? And in this case, we do have the numbers that we need to calculate it. We have that the kinetic energy at 0.1, we need the mass of the skateboarder, got it, and we need the speed at 0.1, got it. Oh, so I can quickly calculate 1/2 times 60 times 8 squared. When I put this into my calculator, I get 1,920 joules. Now, one thing that we need to impress upon you here is that these equations, these formulas, they're honestly just kind of getting us to the starting line. So we have to be pretty quick to be able to do these calculations, to plug into the formula 1/2 m times speed squared and get this number. Now, in the beginning here, we have the PE and the KE. So the total has to be 1,920 joules. PE plus KE, 0 plus 1,920. What about at 0.2? Do we have potential energy? Well, we have a height. And if you have height, you have potential energy. Can we calculate it? Were we given a number? Yeah, we were. So we can figure out that the potential energy at 0.2 is going to be 60, the mass, times g of, we're saying 10, times the height of 1 meter, 60 times 10 times 1. My potential energy is 600 joules. Do we have kinetic energy? Well, the skateboarder is moving here, but we don't know how fast. We are not given the speed. So we have a kinetic energy, but we don't know what it is. So that's an important thing for us to take note of. I don't know the kinetic energy. I know it's not 0. Let's finish out going through our audit. So if I look at point 3, do we have potential energy here? And the answer is yes, because we have height, except I don't know the height. So I know the potential energy isn't 0, but I don't know what the number is. Do we have kinetic energy? Well, since our speed at point 3 is 0, then our kinetic energy at point 3 has to be 0. So kinetic energy is 0, potential energy is unknown. At point 2, potential energy is 600, kinetic energy is unknown. And we have basically framed our question here. Now, there's 2 main ways that students typically like to think about this. Some of them like to set up an equation. So I could take the kinetic energy at point 1 plus the potential energy at point 1. We need to do it for a point where we know both of these equals the kinetic energy at point 2 plus the potential energy at point 2. Again, we were saying our work was 0, no outside forces interfering. So then I can identify that kinetic energy at point 2, that's my unknown. And this equation will only work if I only have one unknown. So when we went through earlier, recognizing that kinetic energy was 0, potential energy, we calculated it, and calculating potential energy at point 2, I have everything. I'm down to one single unknown. So to get my kinetic energy alone, I'm going to zero out the potential energy 1. If it's a 0, I know I'm going to do that. I'm going to subtract my potential energy from both sides to finish getting my kinetic energy alone. And when I solve for that, my kinetic energy at point 2 ends up being kinetic energy 1 minus potential energy 2. Which, when we had the numbers for that, that was 1,920 minus 600 to get 1,320. Now, I said there were 2 main ways that students like doing that. They can set up this equation and solve to get the one alone. The other way that students like doing it is setting up one of these PE, KE, TME grids at each point, PE, KE, TME, because you probably recognized that we said earlier, total mechanical energy has to be the same at all of these points. I could have filled this in, my 1,920, and said 600 plus what equals 1,920, and that also would have given us our 1,320 joules. Let's go ahead and apply that up at position 3. We know, once I know the total mechanical energy at one point, I know it at all my points. 1,920 is my total. What plus 0 equals 1,920? Well, that one is fairly straightforward, but it could have worked if we had other numbers in here as well. So I can figure out that my potential energy at point 3 has to be 1,920 joules. So we have gone through and found numbers for the PE and the KE at all of our points, knowing that the totals had to be the same at every position. We still haven't solved for the speed or the height at position 2 or position 3, but we want to point out to you, if you know the PE or the KE, you can work backwards from what we've done before. Before, if we knew the height, we figured out the PE. But we can go the other way. If I know the KE, if I know the kinetic energy, I could find the speed. So, for example, my speed at point 2, if I want to figure it out, I know that the kinetic energy at point 2 equals 1/2 times the mass times the speed at point 2 squared. If I solve to get my speed alone, we know the mass, we know the kinetic energy, so I can do that. I would multiply both sides by 2. that gets rid of my half. Divide both sides by m. That gets rid of this mass here. And then I would need to square root it to get rid of the v squared. This is a formula that you may want to write down or memorize because it is pretty handy for finding speed, but please be aware. I've seen students go in circles. You need to know the kinetic energy, and that it needs to be the kinetic energy for the point that you're asking about. If I try and put in my kinetic energy from some other point here, it will not tell me the speed. So, in other words, be consistent. Make sure that when you're calculating something, you're comparing apples to apples. I want the speed at position 2. I need the kinetic energy at position 2. This isn't just a magic formula that will spit out speed for anything, anywhere that you want. Okay, well, the kinetic energy that we figured out earlier was 1,320 joules. So when I take 2 times 1,320 and divide that by 60 kilograms, and then square root, then we get a speed of about 6.63 meters per second. I'm going to ask you to pause the video and see if you can figure out what the height at position 3, with the information that we have, can you figure out what the height at position 3 is? So go ahead and pause, and I'll see you here in just a moment. Okay, done? Let's figure out what our height at position 3 is. Just like our kinetic energy can tell us speed, our potential energy can tell us height. So if we ask you to solve for a height, you can consider that to be really prompting you to figure out what the potential energy is, then solve for the height. So we have earlier in this sequence figured out what the potential energy was, and now all we have to do is go backwards in our formula to solve for what the height has to be. By taking potential energy, we figured out that the potential energy at position 3 had to be 1,920 joules divided by the m and the g. So divided by 60 kilograms and divided by about 10 newtons per kilogram. So 1,920 divided by 60 and 10, I get a height of about 3.2 meters. So using conservation of energy, using joules, remember that energy is always in joules, we can come up with plain everyday stuff such as speed in meters per second and height in meters. All right, I hope this helped. And the more you practice these conservation of energy problems, the easier they become, and the more you will be able to see it all around you every day. Thank you for watching, and good luck.